To start by thanking everybody for joining today's Tech Talk featuring Tim Maloney, the co-inventor of the TLP test method. My name is Nick Pipinella from the ESD Association. During this talk, Tim's going to be speaking on his career in all things ESD. At the end of Tim's talk, we're going to open up the floor for questions. During that time, you will be allowed to unmute your microphone and turn on your camera if you'd like to ask your question that way. Otherwise, you can just ask your questions in the chat and somebody will read those off for Tim to answer. If we run out of time for questions and you still have questions at the end, you'll be able to submit those to us via email, so we'll cover that later. You'll want to make sure that you stay until the end of the talk to be entered into our special lucky draw. If you're familiar with our Tech Talks, we've done some of these lucky draws on our previous Tech Talks. This Tech Talk is being sponsored by Botron. The winner will receive a B92900 Elite Sentinel Dual Continuous Monitoring System. So we want to thank Botron for sponsoring this Tech Talk and for providing such a great gift for someone. We'll pass along your information to Botron for the winner, and they'll contact you for your shipping information. So I would now hand it over to Tim to start with his introduction.
Okay, thank you. Let's try to go to my slides. Now let's try to go to the slideshow. Okay, so I'm calling this an ESD-related career in the semiconductor industry. This series is for emerging professionals. I'm a little past emerging, but a lot of you are at that stage, and I want to tell you about how a career path worked out for me and give you some ideas about how to think about your own career, given the fact that it'll be necessary to do a time transformation in some ways. And that's always an interesting exercise as I see it, because you get to think about history. So, let's first briefly look at topics to be covered. I'll do a timeline of my career highlights, summarize, and then look at it in terms of skill acquisition, because the skills you use on one job are used on others. Starting out with your education and so forth. That's an interesting way to approach things as well. Talk about noticing opportunities in your work environment. We'll talk about new engineering developments in the modern world and how they may apply or not. I think everybody can look at their career as some kind of example of a 40-year window, approximately, in history, technological history, and have a look at how that may evolve in a certain 40-year period, and what period that is does make a difference. Okay, so here are my career highlights and milestones. I started out at MIT, Cambridge, Massachusetts. I did a undergraduate degree in physics and had the rare privilege of working alongside in my senior thesis laboratory, working alongside a couple of future Nobel Prize winners. Of course, none of us knew that at the time, but that made things even more tantalizing. This was Professor Kleppner's atomic physics lab, and alongside were a first-year graduate student, Bill Phillips, and also Carl Weinman, who was a sophomore at the time. Very heavy-duty, very fun research group, and I will never forget that experience. And nothing quite like it ever happened, but I was able to take that spirit, I thought, along to my other jobs. So I got an NSF fellowship, and always wondered what it would have been like to go to either Caltech or University of Illinois, the other two graduate student schools that I applied to. But I went to Cornell with an interest in solid state physics, and also I had always had an interest in electrical engineering as an undergraduate, and thought that solid state physics was a way to do experiments and get involved in electronics in some way or other industrially. Ended up doing my PhD in EE, finishing there in 1976, and then spending 18 months or so as a postdoctoral associate in the department, what I called playing professor, managing a research contract, covering for my professor who was on sabbatical, that sort of thing. So by that time, starting out with an interest in what I was comfortable in saying, well, physics, mathematics, electrical engineering, that seemed to be what I was studying all the time as an undergraduate and then as a graduate student. By the time I finished university work, I had background in solid state physics and experimental methods, plus high frequency semiconductor devices and microwave engineering. So I took a job in Silicon Valley at a company that some of you may have heard of, Varian Associates. They had a central research lab then and spent 6.5 years doing more work on microwave devices, did some work on solar cells for NASA. There's a lot of contract work here, a lot of contract work for the government, although it was a commercial company, and I spent my last couple of years working on the company's products in silicon process equipment and so on. At that time, I did something that it could work for you too. You go to future employers, possible future employers, and say, gee, I'm more interested in what our customers are doing than what we as a company are doing. That's why I'm looking for a job here in some kind of transition. So Intel, a semiconductor company that was a Varian customer, Varian made ion implanters, among other things, did hire me into a reliability department, and that's where I started my ESD work. But I had a lot of background for it, with high-speed devices, microwave devices, the electronic devices, solid-state devices, measurement and process, all that stuff I had learned in research work, and was able to continue it there using that background. So all that came into play. Excuse me, on my screen I have to move around this banner of people listed and all that to see my slides. So yeah, I had a bunch of patent opportunities, publication, and so on. Continuing publications after retirement, sometimes with Intel authors, as you know. Now, in terms of skill development, as I promised, I picked up a lot of things on the way. Just as an MIT undergrad, the usual coursework, but also machine shop work for my thesis, on this beam experiment, which included machine shop work, vacuum systems, designing things for that. Also some electronics. Continuing that at Cornell, more machine shop work and vacuum systems, practical electronics, things for the lab. All of us grad students, this was 1970s, all of us grad students worked on our cars. And the car was, that's back when you could work on cars effectively. This was a good way to get design skills, maintenance skills, the kind of thing you need in the laboratory. So that was, that was a useful way to mix it up with other graduate students and sneak some things into the machine shop to learn further skills there as far as developing that aspect. Now, there was one experiment we did, as part of our lab work, exploratory, looking for things to investigate and possibly publish if it was successful. We borrowed and repaired a crude transmission line pulsing setup. This is 1972 for zapping samples of bismuth at low temperature in a magnetic field, hoping to find infrared radiation due to Landau level transitions. Well, we didn't find that, but I learned an interesting technique. I said, gee, this is really neat. You can get pulses, a nanosecond length with, laboratory size lengths of cable and get, many amps at a cost of 50 volts per amp and so on. So Okay, so fast forward to future work on that. Meanwhile, in the EE department a little later at Cornell, I learned things about microwave circuits, high frequency test and measurement equipment, did some computer modeling of physical phenomena in semiconductor devices. Also, well, as a graduate student, learned some computer machine language and programming. Basic computer science that was being encoded in chips at that time, chips that were 4 and 8-bit microprocessors back in the early 70s, but would go on to be what we know later on and today. Also, more work with vacuum systems, culminating with overhauling something to install an E-beam and microwave cavity in vacuum for doing an experiment on looking at semiconductor carrier velocities and so on. That was all good hands-on practice. Then in my job at Varian, Varian was a vacuum company for a long time. And so I did more work on vacuum systems there, including molecular beam epitaxy, other things we don't need to talk about, but my boss even had me set up an E-beam microwave experiment there. That was kind of inherited from Stanford, from some recent work at Stanford where I did more of that E-beam semiconductor carrier velocity work. And in the process also put together high voltage equipment for the E-beam and constructed all of it. So you learn something about static electricity in the process of setting up a high voltage system and insulating yourself from severe shocks. And I found that even if you have a long bakelite knob attached to floating high voltage device, for minuscule current flowing, but still enough current to charge you up, you can get an electrostatic shock when you touch a ground plane. So this was good practical hands-on practice for the ESD world. And I accumulated more skills on process equipment and chemistry, fabricated devices under contract to this and that government entity. And even on the side, some old timers might remember the slight craze for an IEEE microprocessor course back in 1979, where we built a test board and used a Motorola 6800 8-bit processor to do some basic programming and all that. I found with my computer science background and what have you, that was just what I needed to plunge in and get this thing working and do some hands-on work in chips that the likes of which I'd be helping Intel to design in just a few short years. So by the time I came to Intel in 1984, here I'm 34 years old by then, 8 years after my PhD. With all this background, pretty soon I'd be asked, how'd you get all that background? I had fairly young looks then. They thought, a lot of people thought I was a new college graduate, new PhD or something, but I was actually a little older than that and had some industrial research that was like an extension of the academic research. I like playing things that way. That's not for everyone, but it seemed to work out okay. Although, it's kind of a long way to go to get to certain activities that we end up doing. None of it goes to waste. Okay, so all this time, though, I had been a little bit frustrated, being in Silicon Valley, knowing you have to be in the right place at the right time. And it seemed like a lot of us were, out of the mainstream one way or the other. But in my first week at Intel, and I had a feeling I might be able to put 2 and 2 together with this new assignment that I knew I'd have. My first week at Intel, there was an opportunity to use that transmission line technique that I had learned some 12 years earlier in the solid state physics lab at Cornell. Indeed, the technique itself goes back much further. There's even an MIT Rad Lab series book, one of those radar books from World War II, declassified and published around 1948. I think that volume is called Pulse Generators, where they describe this technique. Although for radar pulses, they're more interested in microsecond pulse lengths, and they focused on lumped LC circuits in that case, but they still do treat the continuous transmission line case. So this is what we were able to do and publish by 1985 using the transmission line to get ESD-like square pulses for circuit modeling. So yeah, finally I was in the right place at the right time and was able to introduce this concept to semiconductor reliability, as it were. Back then we didn't have the internet to connect us with all this reference material readily. You had to scrounge around or sneak into the Stanford Library or what have you. You had to know things. You had to have some, experience to put these things together at times. So that's why this was introduced when it was. But sure, it would not have taken very long for someone to do much the same kind of work from some semiconductor company. And once the idea got out there, everybody was doing it. So, I finally lucked out after a lot of blind alleys. I'm fond of saying that, in research, they always say 9 out of 10 ideas fail, they don't work. And sometimes I think I worked on all 9 of those projects. Okay, well, continuing then in the semiconductor industry, just to observe a trend that has become more important in the last number of years. Here's a cartoon that we put up on the wall of a mask designer. I think this is from the New Yorker, and a couple of kids are playing there. And if you can read the caption, this is one child saying to another, "This is just a simulation of what the blocks will look like once they're assembled." And we seem to do more and more of this in the semiconductor industry, doing things what they say, what they call pre-silicon. More and more things are pre-silicon, and less of that hands-on work, less of that required testing of real silicon or even the transmission line pulsing. What's it going to look like when we put things together and do the work? Nonetheless, closure using the transmission line pulsing method is always done, at least to some extent, but we don't have to do quite as much turnaround of our devices and our fab processes and certainly our microprocessors to iterate toward the final product. So if things are tending toward pre-silicon, I found it necessary to know the process, the lab methods, the device and physics and so forth, the test engineering and all that, so that I can mix it up with various people in the process and achieve closure. That's what this is about. Now, jumping to some of my other contributions. Here's a case going back to 2011 where I had the rare privilege of being on the cover of an IEEE magazine. This is an EMC magazine, where it's part of a theme that I developed since 2008 toward until the end of my time with Intel in 2016, and also continuing after that, was that I found I was one of the few people in ESD work to apply basic concepts of pulses and transformations between the time and frequency domain using the Laplace transform to solve these ESD related problems. I always knew they were out there. This goes back to my sophomore year at MIT, and I for a long time thought, well, everything that's been done there has been done. And that was only sort of the case as I realized that we really weren't looking at what goes behind the radiated pulses that come from our CDM tester as well as from real CDM events that happen in in the factory where we might be monitoring them with an antenna. So extension of the pulsed Hertzian dipole to this kind of analysis is the kind of thing that you can hardly even find in the EE related literature, even though in principle it's been around for decades. In practice, It just hasn't been published very much, and yet it happens in front of our face all the time when we look for CDM events, or conveniently appears, from the CDM tester. So that was one of my contributions there. Another thing that emerged in everyday life just a few months ago was it kind of snuck up on me. I had an old Dell Windows 7 personal computer that had been around for about 5 years, waiting for me to throw it out. And before doing so, it's good to remove toxic materials like our city wants us to here in Palo Alto. And I pulled off the back panel, removed the battery, and thought, oh, 3-volt real-time clock battery. Let's see if that still works. I'll put it in my battery drawer. And sure enough, it still works. At which time I realized, oh, wait a minute, I had something to do with the fact that that battery still works, because this has been on real-time clock for 5 years, drawing a small amount of current, but not enough to burn out the battery. Back in 2003, we published this paper on low leakage protection for real-time clock and other pins in the microprocessor that have to draw very low power because they have to operate on a battery like that one about the size of a quarter that you just saw. This is also a patent that was issued. This is how your job comes to closure. It's the personal computer on your own desk where you had a hand in the design, and sometimes those design features become obvious in everyday life. Okay, so let's look a little bit at the skills developed or redeveloped at Intel. I've covered a little bit already, but let's review. So among other things in semiconductor process, I was a fab process reliability engineer in the late 1980s, part of a US-wide group at Intel. They called it the Fab X, where X is one of the numbers, or Fab X reliability engineer, and we'd have meetings of all of us representing the various fabs. Now this was a rare example of a non-ESD assignment of mine, but it was in the same reliability department. And even in that capacity, I managed to horn into some other work going on, and ended up being part of an IRPS best paper in 1990. You can look that up from my publication site. The URL is given later, and I'll show the URL and make these slides available. So at that time, I had a regular meeting with the fab manager, and because of these kind of contributions and having my background, knowing vacuum systems and sputtering equipment and all that from my work at Varian, I could have even transitioned into process engineering at the time. I could have moved to Hudson, Massachusetts when Intel bought digital equipment, things like that. But I stayed in reliability and the ESD work. It's another one of those road not taken episodes. But Intel exposed me to circuit design, logic, finite state machines, instruction sets, device physics. Some of this stuff was peripheral. You end up mixing it up with people who are more deeply into this, but that's a good, it's an ingratiating sort of thing when you can get a good conversation going with people, understanding their point of view, and then folding in the ESD design point of view. So I kept on using, directly or indirectly, the device physics and microwave engineering. Filter theory even, got involved in that work I did on time and frequency domain transforms and so forth. Certainly high frequency test equipment is important even now in the work that I'm doing with payment MSAF at Intel. Other things that were important, again, the signal integrity literature had a lot to do with what I pulled into ESD as far as looking at the characteristics of our pulses, are everything from HPM to CDM to machine model and IEC gun pulses. The concept of Elmore delay, I never formally studied it until I kept seeing it all the time from our designers and realizing, oh, I've got a background in this. This has to do with, the first moment of the, it has to do with, the characteristics of those pulses and what the centroid looks like. And that pulled in network theory. As I was saying, the Laplace and Fourier transforms and their inverses for those conversions, which took me to various tools in Excel, Mathematica, and MATLAB, as we're using now. Okay, then in my last couple of papers at Intel, even got into bringing those concepts into heat flow and thermal resistance, and some of our work for the Industry Council, as well as what's the response to pulsed heat flow as you create with ESD, and some work having to do with design rules for metal at Intel. The feedback and stability theory came into play because you have self-heating of metal. You have a positive temperature coefficient, and that led to two papers at IRPS, 2013 and 2016. And there's even going to be an article for In Compliance magazine that ESD put me up to writing, where I got together with Charvaka Daviri, and we decided that we'd do some kind of reflection on these heat pulse related papers for In Compliance. So that skill development and redevelopment and rediscovery kept things interesting all the time in my 32 years at Intel. Other reflections then, this talk uses a few slides from one that I put on YouTube for STEM students at my old high school back in Ohio, where I mentioned along the way, have some kind of a hook into the arts. And that's worth mentioning to high school students as well as to emerging professionals that might be maybe 10 years older. In my case, it was an easy choice. I was that engineer who can write, and was popular with the patent attorneys because I could write a decent patent disclosure and be good to work with as far as filing the patent. So I dare say some of my patents would not have been selected to be filed as patents if it weren't for the fact that I built up my reputation with the patent attorneys as being somebody that would make it easy for them. So, there's all kinds of things you can do in the arts, such as, theatrical things like giving Zoom presentations on camera. I don't claim to be a great TV star, but some of us have to be. So all those things are, they fold into your job and can make your job more fun and make you more effective out there building your personal brand, as Tom Peters liked to put it. Now, I mentioned a 40-year career window in technology. Well, my 40-year career window, let's say it started with my PhD in 1976, and started to fade out when I left Intel in 2016. I'm not working 7 days a week anymore, and that's that 40-year period. The numbers at either end make a difference because of the technology that existed during that time. So emerging professionals will have a different 40-year window, and the degree of relevance and all that is something that we as amateur historians have to work out, right? Your 40-year window comes into view with a different landscape, and you get to do the time transformation. I myself got to think a fair amount about my own grandfather's technology window, which started in the early part of the last century when he founded a small chemical factory in Mercer County, Ohio. He had a number of products. It was called the Stearic Acid Company, the Salina Stearic Acid Company, but his largest selling product, at least at a certain point, was a lubricant for textile mills in New England that did spinning of wool. Okay, that was a popular product, and it supported his 9 kids and put them through college and all that. But his reason for building it, though, I think is this is a Silicon Valley-like thing to do, right? You have a job and you do the same thing with your own property of your own company. His employer's factory in Syracuse, New York had burned down. So he just wanted his job back. And by that time, he knew how to build the factory, knew how to sell the product and so on, and found some backers in his new wife's family, and he was on his way. Well, that, small chemical factories are not too common anymore, and that faded out after World War II. I guess he was able to support his 9 kids, of course, in the earlier part of that, and also invest in some stocks so that he had some kind of a legacy. But all of us grandkids had to work. Nonetheless, there was a little bit to help us through college. So, to define what you do in tech, I would say your birth year is important, just because that helps define the technology window that you'll be working with. We don't know why your birth year is important. It becomes a little more clear as you get older, but still you will be influenced by historical forces, and it's good to look at those. Now, as examples, after about 20 years of working with one another from different companies, there are 3 of us in the ESD Association that have been on committees for a long time, myself, Robert Ashton, and Mike Shane. After about 20 years of working with each other, we realized we were all born within 2 months of one another back in the summer of 1949. And what does that mean? It meant that actually 1984 was pretty much of a pivotal year, I think, for each of us in different ways, as far as moving into or closer to ESD related work. So, those connections aren't going to happen again, but, something as amusing as that could happen to you. It's often been noted that Bill Gates and Steve Jobs were both born in 1955. That was a good year for personal computer guys to be born. Why was that? I was born before them. They had, I had a 6-year jump on them and I blew it. Why is that? Well, I was in graduate school reading about microprocessors, and if I had dropped out to work on microprocessors, I'm not sure I would have been pulling even with them. In fact, there are enough people who did such a thing and are jealous of those 2 that I don't mind having missed that particular thing. But they were at the right age to make some choices, I think, to get on board with what the microprocessor was going to make possible. A non-technical thing, it's been noted that 3 of our recent American presidents were born in mid-1946. What does that mean? Commentators on TV can't decide what it means, but they think it must mean something. Okay, so how do we find new opportunities? Well, I can recall it in my early years at Intel in the 1980s. They would put us into these counseling sessions with our supervisors and say that we want to help you fulfill long-term career goals at Intel, but you have to meet us at least halfway. You have to be responsible for managing your own career, realizing what your skills are and how they're going to apply now and in the future. And I appreciated that perspective that they can't do everything for you, and we can't do everything for ourselves without a little help from the employer to do that. So, and I would say that is still true. You have to tailor your own career path to try to optimize that, and nobody knows the answers for sure. But you can have a better chance of making a go of it with with your present employer or perhaps another employer by looking at your technology window. That's my idea, not Intel's, but just looking at the possibilities and how the company will evolve. Now, one of the ways you do that is do the obvious, look for adjacencies in your own department. Who are the people who work nearby and what do they do? And, they may be in your staff meeting and you hear about their activities. They could have an interesting perspective. They may even overlap with you in ESD work at times. Certainly my colleagues did, but other colleagues always seem to be nearby, but no formal overlap, but interesting to watch the evolution of their jobs. For example, there always seemed to be somebody not too far away, administratively, if not physically in cube space, of working on product traceability and anti-counterfeit measures for the semiconductor industry. that seems to be put into a reliability department. And I saw that happen over, well, at least since 1990, what's that, 25 years. And the technology kept evolving and the company kept getting more serious about it. And, what they would do would be influenced by that. I'm thinking that, in this space, let's not go into all the details about my thoughts there, but, maybe blockchains have something to do with what we should do about anti-counterfeit, for example. There's always something on the horizon that you read about in magazines that may or may not apply to what you do. So there are a lot of wrong answers of what you read about applying, but once in a while, there's something you should get on board with and talk it up with your associates and discuss what to do. Now, my ESD example of this, as far as adjacencies, is monitoring of ESD events in the factory with antennas, going back to about, in the mid 2000s. Okay, back to 2005. I wrote the paper with Julian Montoya for the symposium where we did some antenna work, and the antenna work kept evolving too. It kept evolving, finishing up with that paper I showed you earlier from the 2011 magazine cover, and there was another one in 2013, and the work goes on even today. So that was a case of what Intel calls assumed responsibility. You see a way to contribute, and you with proper approvals from management and all that start to become involved, and also you need to know when to stop. Sometimes those publication opportunities get a little more intense than the company might want you to take up, but you interact with your managers and you come to an agreement as to what's appropriate and what helps the company, what helps me, and what helps the industry. Those opportunities of adjacencies and assumed responsibility will happen. It's what I was saying about like magazine articles or newly developed tools or things you hear about even on news broadcasts. Those things can be important if you select them carefully because they're brand new. They're not available to your predecessors, so you're not going to find that it's all been done before. It's all reached a break point or an end point before, and any new contributions would have to come from someone more excessively brilliant than your predecessors. You don't like that kind of situation. You want a new thing that's available to you and your contemporaries, and you get to apply it because it's a piece of cake. It's all been, the infrastructure suddenly appears in your hands. Now, a small example that I've used over the last 5 to 7 years, this add-in for Excel called Solver, that sure makes the whole method of Lagrange multipliers idea that I've been using since a college sophomore when I learned it. That certainly makes the optimization of a function subject to constraints an easy thing to do right there in Excel, which we all have loaded on our computers. So I've been able to use that countless times for solving problems, in an hour or so, rather than deciding whether it's worth a week or two of programming to do. Now, a larger trend that ought to be considered, now I have no idea if this is going to apply to ESD work or not, but I can't help but look at all this material, and it's on YouTube. It's MIT courseware that's available to everybody. All this artificial intelligence, neural networks, machine learning, TensorFlow, free computer time available to people to understand enough to put in a few hours to get something off the ground. That's because there's new software infrastructure available for looking at neural network examination of heaps of data. As we know, because of cheap storage and easy acquisition of heaps of data, we need to analyze that data. And possibly the factory ESD thing with heaps of data possibly coming in from antennas, from fixed antenna monitors, looking at antenna waveforms of the sort that I took apart in that 2011 paper. Well, that could be training data for some neural networks. This is a half-baked idea, but that's the idea. Some of these half-baked ideas may work out. It may help to start discussing things maybe at lunch, when we all get back into the office buildings, right? Discuss things and see whether it's worthwhile trying a few, say 1 week experiments, the likes of which you can do through these MIT mini courses. Yeah, there's a 2-week online MIT course you can push yourself through where you get to use some of this free computer time with neural networks. So, ideas like that. There might be some way in which all this artificial intelligence stuff that we read about can be applied to an ESD related assignment, and there could be overlap with your colleagues that you see in staff meeting or in the same department. So yeah, all these concepts of gradient searching and backpropagation and all that are easily accessible compared with what they were a number of years ago. And then finally, as far as looking for opportunities, this has come up several times. For example, in that 2005 paper with Julian Montoya of Intel that I worked with, is statistics. There's a reason why our employers have us do a refresher course in statistics every year or two. I had to do it to get my license to the statistical software renewed. But that was always a good thing to do, and it always came back like, sort of like a foreign language comes back to somebody who was raised in it overseas. I envy those people. They, a couple of days of exposure and they're fluent again. But I was kind of like that with statistics, as are a lot of people that had it in college, had it in grad school, had it with their employers, and yeah, you come back, do a little bit of refresher. Suddenly you're a statistician almost. In the case of that appendix I wrote for Julian's paper, I got with the local statistical expert. Most factories have one or two. This guy was even attended our lunchtime bridge game, so I was easily able to chat him up about statistics and have him review my vocabulary and use of terms and all that in the final write-up to make sure I had that part right and other concepts. So yeah, statistics is something you can fold into your job, virtually every time you recognize that it applies. Well, okay, I guess we've come to the end. My reflections, as I mentioned to the high school students in my STEM talk, the URL is down there and the slides are available too. A good tech job is one where you can regularly advance the thought process and be known for doing so. That's what it's about. You advance the thought process, you get with colleagues to decide the right things to do, and then you apply your skills to what you go off and do to contribute. At least that was my approach, and I've seen that work for others, and it could very likely work for you as well. Yeah, I have my backup slide here. I won't go to my backup slide, but I have more on the Nobel Prize winners that I overlapped with, starting with those MIT guys. I think I'll leave it with that at this point. What do we have? Yeah, we have about 15 minutes. We can go to questions, and if I need my backup slide, I'll go to that.
Perfect. Thank you, Tim. Definitely appreciate that. Very exciting talk. What I'm going to do now is I'm going to go ahead and allow people to turn on their cameras and their microphones to ask questions. You're also welcome to submit your questions in the chat, and I'll read those off for Tim. So you should now have the ability to turn on your cameras and start your videos if you'd like to ask questions. Please just try to not interrupt anybody who's already speaking and try to speak only one at a time. I do have a question here in the chat. How has serving with the ESDA helped you grow in your career and personally?
Oh my. Well, let's see. My ESDA service began in 1984, 85. I attended my first symposium in 84, and with my boss, and my boss promptly diverted inquiries to have Intel participate some more to me. He wanted to do other things and thought this was a good setup for me. So I continued with that. Now, yeah, of course, this was one of those cases where you advance your own career and you make sure that that's agreeable with the employer. So, I got a thumbs up from the employer from the get-go, and that was important. But I thought that the opportunities that were, pretty regularly available to me helped, build my career and contribute to my company kind of synergistically. The standards work. I chaired the HBM standards for a while, and I've worked on standards, as a participant quite a bit. But yeah, the standards have standards work has inspired a number of papers that I wrote along with colleagues, and keeps the ideas coming in various ways. I think the ESD Association as a forum for knowing what's important, generating ideas, getting ideas for new publications, and contributions. That's what's really fulfilling about it, and it seems to contribute to the organization as well. I'm not sure if that's that's kind of what I wanted to talk about. It may not answer the question well enough, but I think if you can see the contributions to the association as synergistic with your employer, given feedback from the employer, you're on the right track. If you find that it's advancing the thought process for you to participate, then you're doing something right.
Thank you for that great question and that great answer. Does anybody else have any other questions?
Let's see, we have 48 participants out there. That's pretty good turnout. Thank you for coming. Well, does something come up on chat there?
Yep, I just had one come through. What ESD demos have you had the most impact with the STEM events at schools?
ESD demo. Well, let's see. The STEM talk to high school students was during the pandemic, and so it was YouTube only. I did it from the same seat in my living room that I'm at right now. So I haven't done demos to STEM students, if that's what your question was. But during the pandemic, we kind of have to make do. Now, if I had gone to the high school, I think I was. I got this invitation to go to the high school just as the pandemic broke out, where I was planning to go back to Ohio to visit friends. I had seen this series, and I told them I could drop by sometime just like these other people, right? And then the pandemic hit, and then we said, well, we should do it on YouTube. Probably more people should do it on YouTube. So we did. My high school, by the way, I had a perfect hook to get going on that talk. If you watch it, our class valedictorian, my friend David Bradley, is the inventor of Control Alt Delete from IBM. He spent his career at IBM after his PhD at Purdue. So I can't top that. But that's what you want if you go out in the industry and make contributions. You kind of back into something that becomes, as Dave once put it in front of Bill Gates, a cultural icon. But that does say something about the prestige of one's employer. Dave wouldn't have had that opportunity if he hadn't been with IBM. IBM wouldn't have gotten Dave if they weren't a prestigious employer. I wouldn't have, yeah, I wanted to mention this about, the ESDA participation. I thought that I got my initial opportunities with ESDA because I worked for Intel. The comparison of, working for Varian, a respected company, but working for Varian versus working for Intel was like night and day as far as how people treat you when you go to a conference. They know the Intel brand when you show up at a conference, and back in the 80s for sure, they want to know, what does Intel think about this? Okay, so you need more going for you than just the fact that you're a good person and people like you. I mean, that's essential, necessary, but not sufficient. Sometimes having an organization behind you can give you the tailwind you need to, be in the right place at the right time.
Great, thank you for that question and for the answer. I do have another question here from the chat. For you, what ESD issue has to be resolved in priority?
Oh, for me, well, I'm retired, so my view of that would be perhaps a little too self-serving. Let me, if you don't mind, if I put myself back, as an Intel employee looking for, what does Intel think? I have to extrapolate, this could be 5 years out of date, but you get, pretty much of a public view of what semiconductor companies think are important. I think, the semiconductor companies just want a smooth process for getting designs, ESD designs folded into new product designs, that is chip designs, smoothly so that they don't have to revise it too many times. Now that was an ongoing process, from the get-go at Intel, get libraries of stuff, get, modular use of stuff. Now, what else is there? Well, I would put a priority on, maybe the factory thing. Now, my colleagues who are actually in the factory might say, oh, this isn't quite as important, but I'd like to see if that data crunching, exercise with factory data ends up being something that's really interesting and important, and above all, easier than ever to do. Okay, it seems to me that a factory outfit with ESD monitoring, antenna monitoring, is going to be collecting heaps of data that doesn't know what to do with before you know it. But if somebody figures out what to do with that data by setting up some computer infrastructure that's more accessible than ever, then there's some kind of a hero. So I would put that as a priority, but maybe a high risk priority. Things might not work out, but the effort expended to find out that it doesn't work is lower than ever. And so that's why you should do it.
Great, thank you for the question and the answer. We do still have a few more minutes for questions. I don't have any further in the chat. So if there's anybody who would like to unmute to ask a question, please feel free to do that now.
I can always go to that Nobel Prize slide if you want to talk about more things, but Jeremy
Smallwood here. How are you doing? Great talk. Thank you very much. I just wanted you mentioned standards and participation in standards, and I think that people tend to sort of think of standards meetings as likely to be fairly boring things if you haven't been involved in them. But I wondered if your experience was anything like mine, which has been, it's actually been a great way of educating myself and learning about technical issues as other people see them, amongst other things. Would you like to comment?
Oh, absolutely. Well, yeah, that's what I tried to get across about saying that standards help advance the thought process, because that's what you're doing. You're getting other people's point of view. And I just love to sit there and listen and not necessarily chime in, because everybody chiming in all at once is bad anyway. So why not be a listener unless I have a compelling reason to talk? But I find it so stimulating. Say I'm working on a slide set, and I can work on the slide set and listen to what people are saying and know and be tuned into both things at once during a standards meeting. It's uncanny how I can be so productive at what sometimes would be tedious, drawing on PowerPoint or something, something kind of mindless but busy work. And suddenly that becomes fascinating because I'm listening to these people talk about something I know about. So, it looks like I'm not paying attention, but I'm paying better attention because I've got some doodling to do on PowerPoint for some reason or other. And this stuff is going on. And once in a while, oh, hey, that's something I know about. You need to hear about this. And, I chime in and then I retreat, to a more appropriate listener status. So, try that sometime, just be a listener. And I hope we have face-to-face meetings where this seems to happen more intensely, but I would say, tap to Zoom if you have to, but try to attend meetings where you have enough technical knowledge, what people are talking about, and don't feel a need to participate heavily, but realize you've learned something and take some notes, whatever it takes to call it a productive exercise. But yeah, I wouldn't know the issues that people were talking about if I didn't sit there and listen and maybe otherwise keep myself occupied doing something that doesn't take a full mind share.
Thank you.
Great. Thank you very much for that question and the answer. So with that, we have run out of time for questions. So to start, I would like to thank Tim Maloney for joining us for this Emerging Professionals Tech Talk. I'd also like to thank everybody for joining and for asking your questions. If at any point you think of any additional questions, you can send those to the ESD Association at info, that's INFO, at ESDA.org, and we'll send off your questions over to Tim. So I want to thank once again Botron for sponsoring today's Tech Talk. So with that, let's start the lucky draw for all of you that have stayed here with us. So Tim, I'm going to ask you to pick a number between 1 to 3, and that will determine how many times I generate a random number, and I'll pick the person who corresponds in the attendee list.
Well, how about 2?